Okay, welcome back, day 4. So here we are. This is what a typical introduction to a unit would look like on my packet. So I'll let you read through this. Okay, and now I'd like to jump in to what all this means. So in this section, we're going to add numerical measures of center and spread to our exploratory data analysis tools. Well, exploratory data analysis can be represented with this flowchart. If we have data as numbers, then we can make a histogram. But once we've made this chart, which we worked on last class, now how do we analyze it? So that is honestly what we're going to be spending the rest of the semester doing, is analyzing numerical data. But that is also what we're going to get into today. So in our toolkit, and so here is a nicer version, and it's all written out. Here, this is skewed to the right. This is normal. This is skewed to the left. Here, so the Babe looks very, very normal. And the bonds, if we get rid of this outlier, looks a little bit skewed to the left. See how the tail goes a little to the left. Okay, the center. So this is going to be replaced today with some better words. But what we wrote before was kind of like where the bump is, or we use this phrase, a typical center. For this one, we could say the majority of data are between 20 and 50. You could have said 30 and 50. For Babe, it was between 40 and 50 was the typical center. And then finally, the spread. So this we will also improve today with different words, but I will always like to use the word spread out or tight. I always like to have a verbal description, just like I like to have a verbal description for spread or skewness. So even though we're going to replace this with numbers, we're always going to still talk about how spread out the data are. That's always going to be really important. So you should have that filled out so that we can jump down to definitions. So the mean is what we think of as the average. Technically, the mean and the median and the mode are different averages. But, in colloquial and slang, we think of the mean as the average. So you basically add them up and divide. If our data were, 2, 3, 5, 5, 8, then we would say 2 plus 3 plus 5 plus 5 plus 8, and then we divide it by how many numbers there are. 1, 2, 3, 4, 5. There are 5 numbers. So 10, 23 over 5, and if I do that math right, that should be 4.6. That's the mean. It also looks like X bar, and it's written as X bar. It is a measure of center. So this will tell you where the center of the data are based on this way of doing it. Another way to find the center is, why not just find the center? So the median is the center number, or the center of an ordered data set. So it has to be ordered. So if it's not ordered, so if it's like 1, 2, 8, 1, 1, 8, 9, 1, 2, 3, that's not ordered. You have to order the data. So we'll take that same thing of 2, 3, 5, 5, and 8. And so what's the middle? This 5, in this case, is the median. And so the median is called X tilde. And it's tilde. Tilde is this little squiggly thing, and it's on the top left-hand part of your keyboard next to the 1. It forms this tilde. So those are our two measures of center. Okay, so you might ask me, Tua, why do I have two measures of center? I'm glad you asked. The mean, you might look at it, is more mathematical than the median, right? Adding them up and dividing versus ordering and find the center. So this is better for us to use mathematically. We can do cooler stuff mathematically with the mean, but the mean is what we call fragile, and we'll learn about that today. It gets affected by weird data points. So the median is a better measure of center. And so you'll see that with houses, they'll talk about the medians. Salaries, they'll talk about the medians. You'll always see them talk about medians because that is a much better measure of center. Unfortunately, we can't do much math. And what you'll realize is basically after today or the next day, we'll be done. Let's play a little with means and medians before we go into measures of spread. So it says choose 5 numbers whose mean equals the median. So this is a fun one to do with groups and all of that, but we'll just do it today. So 5 numbers, and we're going to choose numbers between 0 and 10. You can do repeats. So you can say like 0, 0, 1, 1, 2. And you're going to choose 5 numbers whose mean equals their median. So when you're starting with stuff, maybe we should just experiment. What do you think? Come up with 5 numbers. Do it in your head. All right, what did you come up with? Okay, so I came up with 1, 2, 3, 4, and 5. What is the mean of this data set? 1 plus 2 is 3, is 6, is 10, plus 5 is 15. 15 divided by 5 is 3. Now the median is the middle number. So what's the middle number of this? Right, it's also of an ordered data set. So yes, it is also 3. So is this one where the means equal the median? Absolutely. Okay, what about a different set? 5, 6, 7, 8, and 9. So 5 plus 6 plus 7 plus 8 plus 9, all divided by 5 equals 7. So that's how we got that. And what's the middle number? It is also 7. So that checks out. Okay. But we could do repeats. So we could go like 1, 1, 3, and then 5, 5. Choose numbers whose mean is greater than the median. 1, 2, 3, 4. But let's try 15 instead of 5. So that's 1 plus 2 plus 3 plus 4 plus, but now it's plus 15. And how many numbers are there? 1, 2, 3, 4, 5 data points. So we still just divide it by 5. But now when I add this up, I get 25 over 5, and my mean is 5. So let me ask you, is 5 a number in this set? Not at all. Is 5 close to the middle? Not really, right? If we were to make a histogram of this, we would have a 1, we'd have a 2, we'd have a 3, we'd have a 4, and then we'd have a 15, and 5 is here. So that's where the data are? No, the data are over here, right? But the mean got moved up a little bit because this number got so big. See, when this number was 5, we got an answer of 3. When this number was 15, now the mean moved up to 5. Did the data change much? No, just one number. And yet the mean almost doubled. What about the median? So again, we got 1, 2, 3, 4, 15. That's ordered. What's the median? What's the middle number of that data set? Yes, it is 3. And is 3 a better estimate of where the data are? Absolutely. 3 is right here, right next to all these data. So what's a better measure of center? Right. Let's try it again. Just go 1, 1, 1, 1, 100. 1, 2, 3, 4 ones, and then we've got 100 way out here, right? So if this is our histogram, then you can see that all the numbers are down here at 1. There's this one number at 100, and our measure of center says that the center of the data is at 20.8 right here. Is this where the center of the data are? No. Right? The data are down here, and there's one bump up here. But because there's one bump, it messed it up. Right? We added 100 and to this last number when we add up all these digits, and so that totally messed up our average. Whereas the median, look at the median is still at 1, right here where it should be. So why does this make sense? So this makes sense because the mean is fragile. It's affected by everything. So it's strongly affected by skewness and outliers. So this example, I gave an outlier. Was the outlier big or small? It was a big outlier. Did it make the mean bigger or smaller? It made the mean bigger. If the outlier was smaller, what do you think the mean would do? Yes, the mean would get smaller. So the mean is kind of like the peer pressure. It's affected by peer pressure, right? Everyone's here doing safe stuff. There's one guy here doing something stupid, and the mean goes, oh, I want to see what that guy's doing, and the mean jumps and gets bigger. So that's the mean. The median is the smart one. Maybe it's the older child, right? Firstborn, whatever. Like, always serious. Doesn't move. It's robust. So the median is what we call robust. It doesn't get changed by anything. You might say, well, why not always use the median, Tua? Because the mean is better. Mathematically, we can do more stuff with it, but only if we don't have any strong skewness or outliers. Looking at data that looks like this, would you use the mean or the median if it's skewed? Right, we'd use the median. If it looks like this, where it's normal, would we use the mean or the median? Yes, we could use the median, but what do we want to use? We want to use the mean. Exactly. We could do more math with it. Now, if the data look like this, what would we use, the mean or the median? Okay, I'll give you a quiz. Okay, good. We use the median. How about this? Mean or median? Median. Good. How about this? Mean or median? Median. Okay, here's a trick question. How about this? This one we can still use the mean for because it's still normal. It's not that skewed, right? It looks a little bit skewed, but not like strongly skewed. So if it has a bump or if it's strongly skewed, we have to use the median. Skewness and outliers affect the fragile mean. And the key is that the mean follows the skewness or the outliers. So if the skewness is to the right, which way is the mean going to follow? To the right, and it's going to become bigger or smaller? Bigger. If the outliers are to the right, the mean is going to follow the right, and is it going to be bigger or smaller? Bigger. If the skewness is to the left, and then the median is going to do nothing. It's going to be robust. If there's an outlier to the left, the median is going to do nothing. It'll stay the same. Okay, so I had mentioned that we can now look at histograms, but now we can analyze them. And so we want to analyze these data based on SOCs. But as we analyze them through SOCs, we can note that there could be skewness or it could be normal. So I'm going to write it like this with skewness, or maybe there's an outlier versus something that looks very normal. So if this is skewed, or if there's an outlier, then we can't use the mean, so we have to use the median. Whereas if it is normal, or at least it's symmetric, then usually we can use the mean. Now remember, we always can use the median, so you might say, Tua, why are you making this complicated? Because the mean is what we want to use. But now I'd like to talk about the second aspect of this SOCs, which is how spread out the data are. And to understand how spread out the data are, and why do we care about spread? Well, spread is one of the most important and unique aspects of statistics. It is not talked about in many other fields. It's called the volatility or variability of it. And in real life, the variability is always more important than the actual data point. Like, I don't care how many miles my brake pads get. I care about the variability of that. Meaning, is the person next to me going to have 10,000 miles less than me? Because they got the second one off the lot and I got the first one off the lot. So when you're talking about making chicken McNuggets, how often do you get 9 instead of 10 chicken nuggets? How often is your Coke filled too small, right? So usually in life, it's pretty easy to target things. What's hard is to get accuracy. So accuracy, how consistent are you? That is all about variability. So variability is huge in statistics, and we talk about variability for days. So here we go. Part 2 of this long time with us together is on variability. So look at these 9 distributions. These are 9 different distributions sharing, similar axes. But each of these 9 distributions has the same mean. They all have a mean of 10. You can verify them, but these all have values of 10. So 10, 10, 10, 10. This has a value of 8. What is this value? 8.5. What's the 9? What's the value here? This is 9. And then we have 11, 11.5, and 12. So these are more spread out. And then we have 9, 9.5, 2 9.5s. Right? So if we were to write these out as data, this would be a 9, this would be a 9.5, this would be another 9.5, this would be a 10.5, there'd be another 10.5, and then there'd be an 11. So that's what this data represents, these numbers. So if we were to find the median, 1, 2, 3, 4, 5, 6, we'd have to find the middle between 9.5 and 10.5, right, which is 10. What does the stack of data points for A's dot plot mean? So what does this stack of data points mean for us? So yes, the answer was these are all lined up. These are all the same data point. These data points are all 10, 10, 10, 10, 10, 10. There's 6 tens here. Okay. And it asks, what is its height? So again, this is practicing kind of histograms. The height is 1, 2, 3, 4, 5, 6. It's a height of 6 here. And so it represents that there are 6 data points with a value of 10. Okay, so here's the first set. For this set, I want you, just on your own, to order these from least variability to the greatest variability. So from A, B, C, which do you feel is the least spread out, the most tight, and which do you think is the most spread out? So the least spread out, the most tight is A. That's where all the data are together. And then what's the next one between B and C? Right, is C. C, the data are still close together. And then B, the data are all spread out. Now you might look at that and go, wait a minute, Tua. These data, this looks kind of all jaggedy, right? Down, up, down, up. This looks kind of spread out. Everything's perfect. Why is this? Well, when you think about spread out, what you need to look is left and right, not up and down. So left and right, how many different parts are there? How spread out does it look? This looks like a pancake, and this looks like a skyscraper, right? So this is tight, this is spread out. So what do we know about max and min? What can you do with the max and min? You can minus them, right? And does anyone remember what we called it when we minus the max and min? It's called the range. So the range of the data is the max minus the min. Well, what's the maximum value of here? 10. What's the minimum? 10. So what's 10 minus 10? 0, right? And so that is the range of here. What's the maximum data point here? 12. What's the minimum? 8. So what's 12 minus 8? It's 4. That's why this is more spread out. Now what about here? What's the maximum? 11. What's the minimum? 9. And so we minus those. What do we get? 2. Exactly. So if we were to order these, we would go A, C, B. Done. Awesome, huh? So apply that concept here. So let's apply the range here. Well, the range is 12 minus 8, which is 4. Okay. What's the range here? 12 minus 8, 4. Uh-oh. Same range. What's the range here? 12 minus 4. Uh-oh. Same range. So these have the same range, and yet do you think that these, in fact, they aren't. Order these again, from least to greatest. Take a guess, take a quiz, see how you do. So when we talk about variability, it's variability relative to the center. So how far are these points spread out relative to the center? Well, which one has the least spread? Which one is almost all the data points on the center? E, right? So E is probably going to be the least spread out because all the data points are in the center. No spread here, 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 here. Just one spread here, one over here. What's the next most spread out? That's a little tricky. It happens to be D. Because why? There are still 2 points on the center and the other points aren't far away. How about this one? Now, can you see how far away? This is a point away, that's a point away. So far away. Well, remember, we have to come up with a measuring tool. Well, why don't we measure how far away these points are? Well, how far is this away from the center? That's 0, right? And that's 0. How far is this point away? 1. How far is this point away? 2. How far is this point away? 1. How far is this point away? 2. Well, what can we do? We have a 2, a 1, a 0, 0, 1. What can we do with these numbers to find the total spread? Right, add them up. So if we find the distance from the center to each of these data points and add them up, then that will tell us the total distance. So the total distance to the mean is each data point, x sub I, minus the mean. And now we don't want to deal with negatives, so we'll take the absolute value. So this is negative 1 away, but it becomes 1 away, because of absolute value. So this is the absolute total distance from the mean. So what is this total distance? Well, 0 plus 0 plus 1 plus 2 plus 1 plus 2 is 6. All right, find the total distance here on a quiz. Go. Okay, so this is a whole bunch of zeros, right? 0, 0, 0, 0. And then how far is this? 2. How far is this? 2. So this has a total distance to the mean of 4. Now, how far is this? All right, go for it. Figure it out. Find the number. Okay, so this is 1. We had another 1, and we had a 2. But we had that over here as well. So that's 3 so that's 4 plus 4, which is 8. And so now we have a new version, total distance to the mean. If we find the total distance, it turns out it's the same from all of these. But what isn't the same? What isn't the same amongst all of these? What is different? I mean, sure, the shape is different here, but there's something else that's different. Anyone find it? It's the sample size. Here, the sample size, now I'm going to start using n. How many data points are there? 6. Here, how many data points are there? 8. And here, how many data points are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. No, there's 15 data points. And so, if the total distance is the same, meaning like, you know, this total distance is what? This is, now you got to be careful. This is a change in axes here too. This only went down 1 unit now. So this is 1, 2, 3, 4, 5, 6. So total distance is 6, but there are 6 data points, right? So it only took 6 data points to create a distance of 6. Here, this is a half, 1, 1.5, 2, 3, 4, 5, 6. It also created a distance of 6, but it took 8 data points to do that. 8 people, 8 data points to make that distance of 6. And if you do the math here, you'll find that's also 6, but it took 15 people. So what data is more spread out? Obviously, these are more spread out, but how do we create this into a number? How do we take this 6 and this 6 and make it into one number, and we take this 6 and 15 and make it into a smaller number? And we do it by dividing. If we add up all of these, and we have to add them up, so we need to put a summation here. But now we got to divide it by n, and we divide it by n. 6 divided by 6 is 1. And here, 6 divided by 8 is now 0.75. And here, 6 divided by 15 is 0.4. Now we've got a 0.4, we've got a 0.75, and we've got a 1. Order these, right? So now we've got it as IHG. Whew. So the reason I did this was to tire you out, but also was to impress upon you this concept of spread. Do you see now how things are spread out? See, when they're tight, they look like this. Or when they tie it with a lot of data points, they can look kind of like this. If it's spread out with few data points, it might look like this. Spread out with a lot of data points, it might look like this or like this. So I really want you to look at all of this here. So, can you look at this and go, oh yeah, that looks really tight and it's really small, so I'm going to use the mean on this. Or, oh yeah, this looks really spread out and really messed up, so this is going to be spread out. Or you can look at this and you can say, oh wow, okay, this looks really, really tight. That data looks good. These are great results. If these were vaccines, I'd be very happy. Of course, I'm going to get some variability, but by and large, everything lined up. Right? So this is something I really want you to enjoy and experiment with. But what is the true meaning of all of this? Standard deviation. The true variability of the mean. Remember, we're trying to find this of the mean, not the median, but the true standard deviation of the mean, and that's given by sigma, and it's denoted by this. And we will put this in our notes, and here we are. So the standard deviation of the mean is denoted by sigma, like this. This is how we find it. We take each data point, we minus the mean, except instead of taking the absolute value, we are going to square everything. And of course we take the average, so we've got to divide by n. But because we squared it, how do you undo it? Because why do we square it? Squaring it makes everything positive. So a negative 4 squared becomes positive 16. So remember how we had those negatives and positives? Squaring them is like absolute value, but now we got to undo squaring. How do you undo squaring? We take the square root. So that is the standard deviation. Now, can you imagine memorizing this or doing this? I mean, this would be kind of intense. And yes, there is an exercise here for doing that. Why don't we do it once? Again, you can, if you want to skip through this and not listen to it, you don't have to. But if you'd like to see it all worked out, let me do it once. You will not be tested on this. We have calculators to to do this for us. Okay, so if we were to find this, first we got to find the mean. So what is the mean of this data set? Well, it's 2 plus 3, which is 5, plus 15 is 20. 20 divided by 4 is 5. So the mean is 5. So now we need to find the difference of each of these and square it. So the difference of 2 minus 5 and 3 minus 5 and 6 minus 5 and 9 minus 5. So 2 minus 5 is negative 3 squared, and then 3 minus 5 is negative 2 squared, and then 6 minus 5 is 1 squared, and then 9 minus 5 is 4 squared. So this becomes 9 plus 4 plus 1 plus 16. Alright, so that's 13, 14, that is 30. Okay, so that is our summation of everything squared. So now we've got to divide that by however many data points there are, 4 of them. And then we've got to take the square root. So this is the square root of 7.5. And the square root of 7.5 is 2.74. So that is our standard deviation. Doesn't that suck to do all that? Wouldn't it be nice if we could just take these data, plug it into a calculator, and it tells us? Yay! Well, that, my friends, is what we are going to do. Okay, so this is a part of the course where you need to get a calculator. So this is how you can download a TI calculator and install it on your computer or maybe on your phone. The one I use is called Wabbit Emu. And here it is. So Wabbit Emu emulator, wabbitemulator.org. Here you can download it for Windows. Here you can download it for Android. But if you download this, it'll download an exe file, but you need to open up a ROM. You need an image for it to find. It'll ask you, what's an image? So you can go to tiroms.weebly.com and download whatever ROM you want. I liked the TI-84SE ROM, this one. This is like the Silver Edition Plus. So all I did is just downloaded that file. Then when you open it, it'll ask you to search for the ROM, and all you do is browse for it on your computer. Double click on it, and then you hit finish, and now, my friends, you have a TI calculator. So this is what we'll be using this semester. As with all things, we're going to learn how to use this, and this will go in our toolkit. Notice how it's all open here. There's some basic functions here. Clear will clear everything. You can add things like you normally would, and then you hit enter and it'll tell it to you. If you want to add 5 to 18, you can just hit plus and it'll assume that you want to use the answer from the previous one. Okay, so how are we going to do this? Well, first we need our notes as well. And that, my friends, is here. How to calculate the mean, standard deviation, and quartile. So this will tell you how to find the center and the spread. The two things we were kind of having trouble with. The two things we're like, I wish we had some technology that could help us. This is kind of weird. What is a bump? Boom. Technology will solve all this for us and do it all in a second. Whereas if you had to do this by hand, it would take forever. The first step is everything we do starts with stats. So we're going to hit the stats button. So here, stats button. Bam. Now, we want to edit, right? So we're going to hit enter, which is going to edit, and then we're going to enter the data. So it's already on edit, it's already there. So you don't even have to hit 1, you can just hit enter, and now we enter the data. Well, doesn't this look like a table where you would enter data? Absolutely. So this is 2, 3, 6, 9, that's the data we're going to add. So 2, and then you have to hit enter, 3, enter, and I'm using my keypad, my keyboard, not my mouse, so that's why you're not seeing my mouse move around. So 2, 3, 6, 9, that's it. Okay, so we entered all the data. Now we want to do statistics. What do you think we're going to press? The stat button. Exactly. Now we're going to hit the stat button and actually analyze the data. And so for that, we want to hit calculate. So we hit stat and then we hit right arrow. This is very, very intuitive. How would you move this menu over to here? If there's some button here with an arrow on it, oh yeah, here's one. So if I press that, boom, new data, new menus, right? If I hit here, boom, new menus. But we're just going to go to calculate, and guess what? What's the first thing? One variable statistics. We have one variable we want the stats on. We just have to hit enter, arrow, enter, done. You might have to either hit calculate or enter depending on which ROM you downloaded. But you just kind of go down to calculate, hit the down arrow, you'll get fast at this and hit calculate. And now, bam. What is this? Remember what this was? The average, right? Does the average look like this? What's the average of this? 5. And the standard deviation, drum roll, what did we get? 2.74. And what did we get here? Exactly 2.74. So, my friends, this is exactly how we're going to do this, and this is how we will analyze all of our data from here on out. And now, I'd like to go back, actually, to the point of all of this. Research question, we can't answer, so with English and thinking, so we got to go into math world, convert it into data. As we convert it into data, some of the data are numbers as values. So we've made histograms, we've analyzed it using SOCs. If the data are normal, we can use the mean and standard deviation. Why? Because the mean is fragile and only normal looking data can we use. So the question begs, if instead it is skewed or there's an outlier, then how do we use the median, and what did you mean by inner quartile range? So this will be what we end with. Most critical is that you understand that there is a center and spread. For every data point, there is a measure of center and spread. Look at it this way. If you're trying to hit a target, you can either hit like here with all of your shots, right? Or you could hit here with all of your shots, or you could get here with all of your shots, or finally you could get over here with all of your shots. This is very good precision. So it's tight, the data are tight, however, it's off, right? The center is off, so the center is wrong. Here, the data are tight and it's on target. So this is what you're looking for. It's accurate, it's tight and accurate. Here, it looks spread out, and here is also spread out. The center of this object is around over here. The typical center is around here. The typical center of this object is right in the middle. Typical center of this object is also in the middle. It's kind of over the place, but it's in the middle. So these have the same center, but they have different spreads. See how it can have the same center, different spreads? Or looked another way, you could maybe call this a histogram where all the data are in one spot, and here is a histogram where the data are a little bit more spread out all over the place. But the same center. This center here would be the same as that center here. If this center is at A, then this center will also be at A, right? Whereas this guy, this one will have a very similar histogram to this one. However, it might have a different same spread, I think, as this one, same spread as this one, but maybe its center is off. It's over here instead of back here. So same spread, different center. So we need to understand center versus spread. And so to motivate that, we're going to show this one more way. How do we talk about center and spread using the median and the inner quartile range? We need to do that because we need something for when the data are skew. And you'll find when you do your research or your data, almost all the data come out skew. So you do need to understand this. There's just a trick we'll learn after the next test on how to make everything look like that. And that's why I'm not going so deep into this, but it is something to know. And we're going to do it through Barry Bonds and Babe Ruth. So we want to compare Barry Bonds and Babe Ruth. So these are two histograms. We've compared them before, but you remember how much space they took up to compare it? We needed a huge amount of space, and it was hard. The axes were hard to read. You know, is this on the same as that? It was, and then do you make them the same height? You know, the different heights. Does that matter? All of that kind of throws it off, right? because if you have different sample sizes, your histograms will look different, and that's just because more data was taken with Bonds versus Babe Ruth. But if you have twice as many data points, a histogram is going to look different. That's our motivation. How do we do it? So to do that, we'll go back to the beginning. We've already covered what mean and median are, measures of center. And now we will cover quartiles and 5-number summary, because those are all measures of spread, with the exception of box plot, which is basically like a histogram. Okay, so we've done measures of center, now we're focusing on spread. So to do that, we need toolkit, right? Doesn't that sound like a skill? See, and doesn't your mind go, oh yeah, that's a good idea? And so that's why you have a toolkit designed to help you out in situations like this. So I'm going to start by coming down here in the box plot, and I'm actually going to draw this. So a box plot looks very different from a histogram. It looks like this, and something like that, and sometimes one's longer than the other. So this is called a box plot. This is called the minimum. This right here is called Q1. Here is, can you guess what this is? The center of the data. This is the median. That is Q2. And this is the max. And I'm making space here because you might want to write some more words here, I don't know. But it's also written up here. And what I want you to note is that the 5-number summary and the box plot are identical. Meaning there is absolutely no difference between me saying, hey, the minimum is 5, the Q1, the median is 10, Q3 is 15, and the max is 30. There's no difference between me saying those 5 numbers and me drawing this. And that's because this plot only shows 5 points. All it does is it takes those 5 points and puts them on a number line and puts some little boxes around them. Okay, so what are those boxes? Well, this is the inner quartile range. This is a measure of what? Spread. This is the distance from Q1 up to Q3. So that's the inner quartile range. So I don't have that listed here under quartiles, but I'll just say it. So Q3 minus Q1 equals the inner quartile range IQR. You remember this tilde splits the data in half, right? So half is what as a percent? It's 50 as a percent, right? So half the data is below this and half is above. Now this gets tricky because you're like, wait a minute, Tua, there's a lot less room here than here. Well, that just means that the data may be more stacked here. So we'll get into that later, especially with the homework and whatnot. This gets a little tricky. But suffice it to say that half the data is below because, remember, the median is the middle of an ordered data set. It's the middle number, and so therefore half has to be below. Well, Q1 is just the median of the lower half. So what's half of 50%? Exactly, 25%. So there is 25% in each one of these boxes. So if we write another one out here, or maybe you were smart and made two of these made one big box, but there's 25% of the data here, 25% of the data here, 25% of the data here, 25% of the data here. This will be on various homeworks, quizzes, and that kind of stuff. Why? Because one of the student learning outcomes is to understand area and probability, and that's what percentages come in. But also, remember, we're trying to understand where the middle of the data are. Well, if I just said, hey, Mr. Boss, Mrs. Boss, the center of my data, the middle 50% of my data is between this number and this number, wouldn't that look good, right? So we need to talk about center and spread, and we've done it, my friends. Now let's do it in the application. Okay, so here we are. We now need to make a box plot for this. So so if we want to make a box plot out of this, it's the same as before. We have to enter the data, we have to calculate the numbers, and then we have to plot the results. So we need to input all of these data into our calculator. So here we go. What do we do? What do we hit first after the on button? So we can clear it if we like. We go to stat, and then what? Enter for edit. Now all the data are here. We want to get rid of it. Hit the up arrow. Now we're on the list, and it shows the list here. Don't hit delete. If you hit delete, it's going to get rid of it, and then you have to reset your thing. You can just close it and open it, or second memory, reset, yes, yes, and now you're fine. And now you've got your L1 back. But here we go. Let's input the data. So 16, 25, good. So now that all the data are entered, so if we wanted to write this down, we could say, just in case you want to have these steps for later, I don't know. The first step is to enter data. And then the second step is to do the 5-number summary, or the box plot. And we get that just like we got our standard deviation. And then the last step is we basically plot it. So not too much, you're right, that's why I didn't worry too much here, but there's not too much to show. We're going to go from 0 all the way up to 73. So if we start at 0, go up by 10s, 10, 20, 30, 40, 50, 60, 70, 80. All right. So all we do is go to stat. Now what do we do next? Remember? We go to calculate. And what are we calculating? The 1var stats. So we just go down and hit calculate, and bam. So you might not see the min, median, but guess what? There's a down arrow. So you hit the down arrow, and there you are. Voila. All of it. So the min is 5. Q1 is 25. The median is 34. Q3 is 45. And the max is 73. Let's plot that. So 5, 10, 22 is right around here. Goes up to 25. Very, very tight. And then it goes all the way up to 34, where that's the median. It goes all the way up to 45. That's Q3. And then finally there's a max at 73. Now this I kind of know it's not really a max, it's an outlier. So I'm going to put an outlier up here at 73. And then the next highest number is about, it looks like 46. 46 is right above, one above 45, so it goes right to there. And then there's this outlier here, which usually we draw as a dot. The other reason I don't like drawing box plots is because we have to deal with things like these outliers, and there's rules for it, and I just don't want to get into it. You know, there's only so much we can cover. So that's bonds. Now let's do the babe. So I can do something fancy. We can go to stat, and we can go to edit, but this time we can hit over and go to L2 and input the data in L2. Okay, so that all lines up. And now we can, what do? You remember? Stat, right? We don't have to clear, just stat. And then what? Calculate. Good. And then what? Enter. You got it, right? Now you've learned technology. So we go to stat and calculate and enter, but now we got to be careful. Remember we put this in L2, we were sneaky. So this got to be L2. See how this shows alpha already? It's already using alpha. I need it to use second. So I need to hit the second button, that's shift. And now I want to capture L2, so I hit 2, bam. So that's if you want to be fancy. Otherwise you can just delete the data and put the data back and then run it normal. So this is our 5-number summary for Babe Ruth. Notice these data are much tighter than they are for the Babe. The min starts at 22, similar to the Babe. Okay, so the Babe starts at 22, goes up to 35 for our Q1, then shoots all the way up to 46 for our median, finally shoots up to 54. Look at that, clear past Barry Bonds for the Q3, and then all the way up to 60 to capture everything. So this is the Babe. So looking at this, can you see that Babe was edging out from Bonds? So Babes was a little better than Bonds, but there was years when Bonds was better, right? All of these years, Bonds was better than all of these years for the Babe, right? But so there's some discrepancies here we could talk about. Let's talk about percentages. What percent of the time did Barry Bonds hit below about a 35? Right, 10, 20, 30, around a 35. What percent did Barry Bonds hit below that? 50% of the time he hit below 35 home runs. So if you were betting on Bonds hitting above 35, 50% of the time you'd be wrong. Whereas the Babe, what percent of the time does he get below 35 home runs? What percent is in this tail? 25%. So only 25% of the time does Babe hit less than 35 home runs. Every other game every other season in his life, he's hit more. 75% of his games hit more than 35 or so home runs. That's pretty amazing, right? So you can kind of start comparing these, but do you notice how there's this overlap here? Overlap between the two. It's not like Bonds is way back here and Babe is, I mean, these are both home run kings, right? If I was batting, I'd be down here. Most people are down here getting, a few home runs a year. These guys are getting 20, 30, 40 home runs. Is incredible. So both of them are great. They're awesome compared to everyone else, but perhaps the Babe is a little bit more consistent and a little bit better than Bonds, even though Bonds is the home run king with 73 in 1 year. Okay, I'd like to take a second to go over this homework. This homework is very, very, very difficult, and it throws students off. It's probably one of the hardest homework assignments you'll get in this semester. This is from that book I was talking about, so don't blame me. But it's a wonderful homework assignment because it really helps you understand it. So in the discussions, please talk about this homework assignment and ask questions. I don't call it cheating if you guys ask each other for help on this. What'd you get? How'd you do it? Well, I don't understand. Show me what you did. Can you explain it to me? Perfect. What'd you get for this? How'd you do it? Just follow up with them on how'd you do it. I don't understand. But that's great, and I hope you feel comfortable asking each other for that. I'll be absolutely having people be talking about that in our discussions if I haven't already done so. So when you're looking at something like this, I always gravitate toward the graph. So without even reading any of this stuff, notice how this is not in percentages. First thing you want to do is turn this into a percentage. So this is 40%. This is 10%. This is infant mortality. Infant mortality is this weird word where it's how many infants die per 1,000 live births. What are the individuals here? So now let's read it. The infant mortality rate is defined as the number of infant deaths per 1,000 live births. This is often as an indicator for the health level in a country. What does each one of these dots represent? A country. So like that one's the U.S., this one's Afghanistan, this one's Herzegovina, Libya, whatever. All these countries up here, and then some of the higher infant mortality countries are up at the end. So each one of these is a country. So what's our variable? What's our individual? A country. What is the variable we're looking at? A country's infant mortality rate. And so this is a bar chart or a histogram? It's a histogram. But what are we talking about? We're talking about box plots. So we're comparing box plots to histograms. Awesome stuff, very, very difficult. So if you want to draw a box plot on here, well, the box plot's going to start here, it's going to go up somewhere, and it's going to end here, right? So you just need to figure out where the box goes. To find the first line in the box, we need to find what Q1 is. So Q1 is what percent of the data? Q1 represents the first 25% of the data. Well, what percent of the data are represented here in this bar? The first 35%. So is Q1 represented in this data set? Absolutely. Q1 exists here. So I can actually erase this and rewrite it and say, nope, my box plot goes down here and actually has its Q1 right in there. So the median is what? 50%. So is 50% here? Nope, this is just the first 35%. So is the median here? Maybe, maybe not. And then Q3 would be the 75%. So draw your box plot here. And when you draw it, that'll allow you to estimate it. Here, this is between 0 and 10. Q1 is between 0 to 10. That's the answer for A for Q1. Then you'd say, what's Q2? What's Q3? Now, this is a question on skewness. If it's skewed to the right, is the mean bigger or smaller? Go back to your notes. Here's one, this I love. This is a beautiful one. Can you match these? So A goes to what? 1, 2, or 3. This one, the key is you have 400 observers. If you have 400 observers, then where's the median? The 200th observer is the median. So this represents how many? Maybe the first, the top 10. So this would represent the 391st observation all the way up to the very last 400th observation. So if we were to order these observations, we would have like a 41, maybe a 42, a 43, and like 400 observations later, we'd have a maybe a 99, and maybe we'd have a 99. Maybe no one got 100, but we got a couple 99s. So we order all of those, and then we're trying to find where is the 200th one. So this is the first 10. That's not containing the 200th one. So let's go down another. How much? Another maybe 50. So that's now down to 341 to 390. Does that contain the 300th one? No. So we keep going down till you can find out. Is it between 85 and 90, 80 and 85, or so on? Next. So this is lab work. So this is something where, yes, you can get help in the lab. Right now, I don't suggest getting help in the lab. No one's going to be able to help you. This is very, very difficult work, and most professors can't help with this, so I got to help you. And so we'll do this a little bit here, and then you'll get help in the discussion. For each, state the following whether you'd expect the distribution to be symmetric, right skewed, or left skewed. Symmetric, we're just going to say the same is basically normal. It's technically not the same, but it's okay for this class. Number of pets in a household. So if you were to estimate number of pets in a household, how would you do that? So how many, let's say I have 0 pets, right? Say someone else has 5 pets. Someone else has 0 pets. Someone else has 0 pets. Someone else has 2. So you'd expect a lot of people to have 0 pets, right? Maybe there's more people with 1 pet, less people with 2 pets, very few people with 3 pets, and then you get like the weird ones out here that may have a few pets. No, I'm kidding. Animals are lovely. So what kind of distribution is this? Is this skewed right or skewed left? So that's how you want to answer that. And if it's skewed, do we use the mean and standard deviation, or do we use the median and the IQR? So if it's normal, we use the mean and standard deviation. If it's skewed, then it's the IQR. So an answer for this I would expect would be the word standard deviation or the word IQR. Here I expect the word to be standard deviation or IQR. That's all I'm looking for is the answer. Same with these. But again, to do this, it helps to draw this. So again, draw a line, draw a number line. These are median. These are housing prices. They go from below 350,000 all the way up to 6 million. So if we were to write that as 0, this would be 1 million, 2 million, 3 million, 4 million, 5 million, 6 million. 25% are below 350. So from not 0, but from somewhere below 350 up to 350 is the first 25% of these homes. Then from 350 to 450 captures the median. But then 75% of the homes is at 1 million. So way up here is 1 million. And then we got some homes way past 6 million. So we don't know how high this goes. But we definitely have some outliers up here. So if you look at this, is this a skewed graph? Is it skewed right or skewed left? Or is it normal and symmetric? If it's skewed, should I use the mean and standard deviation or the IQR? Which one? All right. So that, my friends, is the homework. And with that, I bid you adieu.